Now that we're recorded, again, hello everybody. Welcome to the Neocortex Introductory Webinar. I'm Nick Nystrom. I'm Chief Scientist at PSC and part of the Neocortex project. I'd just like to make a few preliminary statements as we get started. First of all, this meeting will be recorded. It is being recorded, and we'll be posting it to YouTube next week. So if you can't make it for the whole thing, or if you have colleagues, please refer them. We're planning on about 40 minutes presentation followed by Q&A. If you have questions, please submit them to the Zoom chat. We're monitoring those during the webinar, and we'll be answering those in a combination of Zoom chat, some live, and for those we can't get to today, we'll be following up and answering them online on the Neocortex website. Please participate. We'll be having several polls during the webinar to get feedback on what you're interested in and how we can help you. Because this is an XSEED webinar, XSEED is a National Science Foundation virtual organization overseeing our cyber infrastructure. We ask that you abide by the XSEED Code of Conduct. And it's common sense. It says this is inclusive, no harassment policy, and welcoming to everybody, really embracing diversity, inclusion, as we do in our Neocortex project. So please take a moment to read this and take note. And with that, I would like to introduce our Neocortex principal investigator, Paola Burtrago, who will begin this presentation.
Thank you, Nick. Can you hear me well?
Very well.
Well, thank you all for joining this webinar. As Nick has mentioned, we are going to be talking about Neocortex, which is an NSF-funded upcoming supercomputer. The content today will be delivered in cooperation or in collaboration with Nick. We'll be talking about the infrastructure part in detail. So let's get started. This is our outline. We are going to have an introduction where we will be talking about the context or what's the environment in which Neocortex was designed and envisioned. Then we will be talking about a little bit also the motivation, why Neocortex and where do we see Neocortex helping our research community. Then we will be talking about introducing in more detail what Neocortex is, and then what are the kind of applications we expect to target. And then, as I mentioned, Nick will be doing a deeper dive on the system architecture. Next, we will be talking about the early user program, which is the way in which each and all of you can be part of this project and help us make this a great success. Later on, we will have a summary and we will be opening ideally a 20-minute period of time for Q&A. So, introduction. I would like to start by setting a little bit of the context. Neocortex is a project that was proposed in response to the NSF solicitation 19507. The number is not necessarily that important. What I would like to highlight here is that normally when we are talking about the cyber infrastructure landscape that is funded by NSF, we tend to think of systems that are normally described as capacity systems, which are production-ready systems that are expected to serve the national open science community. Now, starting last year in 2019, NSF started calling or requesting a type of system that is referred to as category 2 and refers to innovative prototypes or testbeds. And these systems are aimed to capture forward-looking capabilities that, as the text says in the bottom, deploys novel technologies, architectures, usage models, and also targets the exploration of new applications, algorithms, or paradigms. All of these in the aims of fostering scientific discovery in science and engineering. So Neocortex is a category 2 type of system. Of these systems, there have been awarded only 3 so far. One last year, UCAMI, and then SDSC, Voyager this year, and then Neocortex, which will be delivered by the Pittsburgh Supercomputing Center. So this is a new category of system. It's more flexible, it's more exploratory, and it's all about exploring new venues or approaches to make science happen. So Neocortex was awarded earlier this year as in the same way that Bridges AI and Bridges 2, Neocortex is NSF funded, is once again a category 2 system, and is delivered in collaboration with Cerebras and Hewlett Packard Enterprise. We will go into more detail to describe how this collaboration works. Certainly they are providing parts of the supercomputing, but also we are collaborating to make sure the system satisfy the needs of our user base. In this slide, what I would like to present is what are the 3 main goals or overarching goals of the project Neocortex. The first goal is to deploy the supercomputer. We are planning to do that this year, around late summer or fall, early fall. And then with deploying the system, what we aim to do is we aim to bring or offer to the national open science community hardware technology that is going to accelerate AI training, that is going to enable researchers, students, and faculty and whatnot to explore AI without the boundaries that maybe they currently have by not having access to advanced computing powers and memory and data movement or fast data movement. So that's one of the main goals. The second one is that this is a project that is expected to last 5 years, during which we will be exploring how a Neocortex can better serve our community, and we will be offering support and operating Neocortex. Third, and very important goal for this project, we will be engaging a wide audience in our open science community, and we will fostering adoption, all of these via outreach, training, and content and knowledge dissemination. So now let's jump a little bit to the motivation. Many of you, I presume, might be familiar with this graph. This is a study done by OpenAI, published last year. That's when we deploy or when we copy this graph. It has been around and has been constantly updated. But what it shows, and what we have here on this graph, each of these points is an AI model. And in the vertical axis, what we have is the number of petaflops days that are required to train this model. So we see they tend to be, or these models are the state-of-the-art models in different times over the years. So what we can see, or what is interesting to highlight from here, is that from 1960 until a little bit past 2010, more exactly 2012, we see that there is a line that has a certain inclination that closely tracks Moore's law. So in a way, we were seeing that the most demanding artificial intelligence models were requiring compute that was doubling every 2 years. Now in 2012, we started seeing how all these very interesting deep learning models, the compute required to train them started doubling every 3.4 months. So that clearly calls for a different approach to satisfying this compute or ever-growing hunger for compute. Another example of how we see that artificial intelligence is just growing and growing in terms of complexity and in terms of the hardware specifications that are needed to enable it are on the left. We have models that are used for image classification. In particular, we are talking about image classification with ImageNet. Vertical axis, we are talking about top 5 accuracy. Each of the circles represents the size of the model. So where we have models that use 1 million parameters and up to a few 100 million parameters. We can see also on the horizontal axis the number of operations required to execute just one forward pass. And there is a clear correlation in terms of the compute required to train them and the accuracy that they deliver. This is on the left when we talk about computer vision. On the right, we can see some transformer type of networks that are normally using natural language processing. And once again, when we look at the column that we label as parameters, we can see how the number of parameters just have, there's a growing tendency. So for a few hundred of millions, which is in itself a very large model, now we see that we have a few hundred billions with GPT-3, which was published last month this year. So if we look at the models in isolation, we see there is a growing demand for larger memory, more compute to be able to train them. Now, if we consider additional sources of complexity, because when you are training or doing research in deep learning, you don't just have data trained and then you're ready to go. There are different approaches like generative adversarial learning, domain adaptation, reinforcement learning that by default relied in an iterative approach where you train multiple times before you reach a final version of your model. So we are talking about very complex model that you have to constantly train. On top of that, and well, this kind of reiterates that need. Normally with machine learning workflows, you just have so many stages or steps that you need to involve when you're training your model. It's not only just train and go, there is a pre-processing step that tends to be very time consuming and effort consuming in terms of the talent that is developing these models. So you have raw data, you have to do pre-processing, then when you have the data and in a clean, curated form, then you can explore training. But then training actually has different steps. And then once you train one time, you have to go back again many times, either because you got new data or because you're doing some hyperparameter optimization or you're doing network architecture research. So many reasons why you might need to go around. And so this just goes to say the need for compute that would allow to advance research enabled by AI is definitely there, and it's just growing and increasing over time. Now, just to reiterate this sentence, there is this paper published by Jan LeCun, one of the most popular researchers in the AI landscape and creator of the CNNs. He last year put together a paper called Past, Present, and Future of Deep Learning Harvard. We have the link here, well, not the link, but you can find it, and I recommend you read it if you're interested in seeing how Harvard motivates and limits the type of ideas that are explored by AI researchers. It's just a reality, and that's what happened in 2012 when a new approach to Harvard, and also a combination of having the data and also the algorithms. In 2012, when new Harvard was enabled and for or used for artificial intelligence models that had been developed decades ago, were now possible to implement. It was now possible to implement them, and then the revolution of artificial intelligence started. So what we are aiming here is to continue that revolution and maybe sort of enabling a second wave. Now, the first quote, what mentions is that how Harvard limits what is explored. Also, the second quote just goes to say that in deep learning, when we are talking about supervised learning, the tendency is to use larger and larger models. Now, an area of deep learning or machine learning that is being explored, but is not as mature as supervised learning is what we would refer to as unsupervised learning or self-supervised, weakly supervised, or multitask learning. Those are areas that are slightly more complex, where definitely larger networks would be needed to produce good results. So that's the current landscape that we have in AI research or research enabled by AI. And that's what motivated Neocortex. Now, just to make it more explicit, who did we design the system for? Certainly people doing demanding deep learning training, people that are already hitting the limits of the current systems available at the time. And also considering that the way Neocortex is going to be deployed, we are considering or targeting users that have scientific workflows that in which one part is deep learning models, or they have a stage that is deep learning, but also might be doing simulations where deep learning can come in the form of surrogate model. So considering Neocortex is going to be integrated with Bridges 2, ideal candidates or users for this new system would be users that have complementary parts of the workflow leveraging Bridges 2 resources. So some examples include computer vision using for medical research. So research done with large sets of medical images, applications where the resolution of these medical images is needed to produce good results. We also can consider challenging training in astrophysics, weather, genomics, or other science. So all these applications then currently might be bounded by memory at the time, or might be bounded by just the length that it takes to train. Those are what we are aiming for. And as I mentioned, workflows that include simulation runs and where deep learning models could potentially be used as surrogate models. Other type of models that would fit this kind of supercomputer that we're bringing are models that are dynamic, or models with separable convolutions, models where sparsity is induced in particular, and Nick will talk about that in a little bit more detail. This system that we are deploying is excellent at exploiting sparsity that is very present in deep learning models at the time, and is exploits this in a very interesting way in which you don't perform operations, you don't waste energy and time computing or upgrades or gradings where you have zeros. Other type of models that we are targeting are graph neural networks, models with sparse attention, sequential models, and the last one, which is very important, models that would benefit, and maybe not only benefit, but models that demand model parallelism to be trained. So with that in mind, we are introducing Neocortex. This is, again, a system that is designed to accelerate scientific discovery. Our target is to shorten by several orders of magnitude the time required for demanding deep learning training. Our target is to make it as close as interactive as possible. We certainly understand how the cycle of from deciding an experiment up to the moment that you get results and then you iterate, that drives the speed at which you can produce results, and is a current limitation for many of our users. We also want to foster integration of artificial deep learning with scientific workflows. As I mentioned, a Neocortex will be integrated with Bridges 2 and want to leverage that part. And then we will be providing this revolutionary new hardware that will hopefully enable the design of new algorithms and networks altogether by breaking some of the boundaries that currently exist regarding hardware. This system is offered at no cost, so it's completely free of charge to anybody that falls under this category of national open science community. So if you're a student or you're a researcher affiliated with an academic institution, you most likely will be able to have an access free of charge to the system, which is very revolutionizing in the way that we will be democratizing access to revolutionizing or very powerful compute for artificial intelligence. Now, there is this disclaimer that potential users that are interested in this system and don't necessarily follow under this class, there is also a way we can get or explore working together, and we will have to handle it on a case-by-case basis. So I encourage you to get in contact if you're interested in getting access to the system and don't necessarily follow on the open science category. So Neocortex, as you guys might have imagined, was inspired, the name was inspired by this great part of our brain that is known to have evolved more recently and is involved with the processing of sensory data, including visual data, audio data, and also with decisions such as movement in our body. So we are aiming and hoping that with our system, we will be enable something similar to what this part of our brain does, which takes a lot of sensory data and helps make decisions and produce great results in a specific machine learning task. So now let's go and talk a little bit more about the resources specification. And here I would like to hand over to Nick. Nick, please take it from here.
Okay, thank you, Paula. So I hope everybody's been excited about what they've heard on the why Cerebrus and Neocortex are what they are. Excuse me. I'd like to tell you a bit about the hardware. So we designed this in collaboration with Cerebrus Systems and Hewlett-Packard Enterprise. And you may have seen a lot of press that's been out since last fall about the Cerebrus CS1 and the wafer scale engine being the most powerful AI system on the planet. And it is. So when we were designing Neocortex, we were thinking about what can we do that would make it even better? And the answer is that no matter how great a system is, it's never big enough to do everything you could ever imagine. So we wanted to be able to explore scaling it beyond one CS1 to more than one. And so 2 is the right number to begin. We also wanted to exploit what we know about high performance computing architecture to be able to drive these at extremely high speed, either independently, each CS1 independently, or together, using them both at once, again, at full speed. So we did that with an HPE Superdome Flex. This is a very large shared memory server. It builds on experience we have at PSC. And we've been working with HP Labs to design it to be balanced with the 2 CS1s. So that's the compute nodes. It's 2 CS1s and the Superdome. We'll get into more detail about each of those in a moment. The interconnect is 100 gigabit Ethernet links, and between each Superdome Flex and the Superdome, there are 12 of these. So 1.2 terabits to each CS1. That's 150 gigabytes per second. Really phenomenal connectivity. And then we pair that with 8 HDR200 links to Bridges 2. Now, Bridges 2 is the other supercomputer we're deploying this year. And so I'm PI of that. Paula's co-PI of it. And Sergio, who's in the audience, is also a co-PI of that project. The point here is that Bridges 2 provides additional storage, 15 petabytes of disk, tremendous amounts of general purpose computing, traditional machine learning. And so it gives a complete ecosystem for this amazing deep learning training environment that is Neocortex. The storage, can you back up one slide, please? The storage is very rich. There's 205 terabytes of NVMe SSD within the Superdome Flex. That's local to Neocortex. There's 24 terabytes of RAM on that server as well. That's the biggest system PSC has ever deployed. And that connects to roughly 15 petabytes on Lustre on Bridges for storing really large data. Next slide, please. So the CS1 server is shown in this CAD cutaway view. It's a 15 rack unit high server, so about half a normal rack, roughly, maybe a third. It's impressive. It has very extensive water cooling to keep this processor at operating temperatures. The processor is shown on the right. For those not familiar with American baseball, that's a baseball. It's about the size you can fit in your hand comfortably. And so the processor is essentially as large as you can make on a silicon wafer. And that's what we're looking at here. That's why it's called the wafer scale engine. Now, the vision Cerebrus had was by designing a processor specifically for sparsity and the operations we need to do for deep learning training and some other things, you can really optimize the operations. You can avoid doing very expensive multiplies by 0 that dominate most of the operations on competing architectures. And you can focus the floating point operations onto only operations that you need to do to get a result. The interconnect on the wafer is also reconfigurable. that reconfigurability is essential because you have to get the yield up on this whole wafer scale processor, and being able to reconfigure around any defect in the silicon is essential to get close to 100% yield on these wafers. And the last thing is the memory is on board. So this next slide, yep, thank you for moving me along. Next slide is an image. This is actually from a while ago in Los Gatos at the Cerebras facility in California. And these are two of the systems. The engineering is just, I would say, exquisite. The cooling is, as I said, it's a dual loop cooling system. There's one enclosed loop, and then that connects to a separate external chilled water loop. And that's needed because these processors can run up to about 20 kilowatts. And so that's a lot of cooling to handle. We have the front view on the left, the back view on the right, and these can be connected. The 12 times 100 gigabit Ethernets are what come out the back, and we'll go into the Superdome. In Neocortex at PSC, this will be a 2-rack system, the Cerebras in 1 rack, and then the Superdome Flex next door. Argonne had deployed one of these before the Supercomputing Conference last November. And they received, as far as I know, the first one that was publicly announced. This is led by Rick Stevens, who you may know from doing very impressive work in cancer research and other fields. And so they were a very early adopter of this. They've been working closely with Cerebras. There's been also a system deployed at Lawrence Livermore National Laboratory. As far as I know, PSC is the first to receive a system that will contain 2 of these operating together, and that's really exciting for the open research community. Next slide, please. So I'd like to speak a little bit about the wafer scale engine, or WSE. It's the largest chip ever built. It's over 46,000 square millimeters of silicon and 1.2 trillion transistors. For comparison, if you read about modern high-end CPUs and GPUs, they are typically in the billions of transistors. So this is on the order of 1,000 times bigger, at least 100 times bigger than the very biggest things being built now. It has 400,000 AI optimized cores. Now these are the cores that are optimized to be able to do sparse arithmetic on tensor operations.
Turn it off, but she says that she just doesn't have the moment.
Amanda, can you mute everybody, please? Thank you. Now, something very significant about this processor is that it contains 18 gigabytes of SRAM. For those familiar with computer engineering, SRAM is static RAM. It's exceedingly fast. It's also exceedingly expensive. That's why you don't find it on normal processors except in the very tiny caches. But on the wafer scale engine, we have 18 gigabytes of SRAM. On typical processors, that is in the kilobytes. Here we have gigabytes. So again, a factor of hundreds of thousands bigger. And what that means is that because it's distributed across the wafer scale engine, the SRAM is also accessible in only 1 clock cycle from the cores. Compare that to L1 cache on normal processors. That's typically a few clock cycles. So what that means is very fast to get this sparse data into the processors. And the bandwidth of that SRAM is 9 petabytes per second of memory bandwidth. Again, if you want to compare that to modern high-end CPUs as we're deploying in Bridges 2, they're fantastic, but they're on the order of 200 gigabytes per second. And between gigabytes, you have terabytes. And so we have many orders of magnitude difference in the memory bandwidth. And the final piece of this is the fabric bandwidth. Now the fabric is the interconnect that is actually on the wafer scale engine that's moving data around the die. And that number is 100 petabits. That's just mind-boggling. In doing a lot of HPC over a long time at PSC, I haven't seen numbers anywhere like this. And so that's what we learned about Cerebras. We became very excited by this chip and its potential. I think in my history of building high-performance computing systems, this is the single most transformative step that has been taken. And I think the exploration we're doing for deep learning with Neocortex and Cerebrus and HP Labs, I think it may set the tone for other architectural trends to come. So the system I/O on the unit, the CS1, is 1.2 terabits, so 12 times 100 gigabits per second. The power is 20 kilowatts. And what's really exciting here isn't just the frameworks we all know and love, TensorFlow and PyTorch. So that makes it easy to use despite the exotic hardware that is under the hood. Next slide, please. The wafer scale engine is a fully programmable system that is handled internally by the Cerebrus software and compiler stack. So this makes it transparent to the users. These are what ingest the models that are expressed in TensorFlow or PyTorch. And behind the scenes, there's a graph compiler that decomposes the logic into something that maps onto the silicon. And at the lowest level, it actually looks like a place and route that you would do for mapping out transistors on a die or an FPGA. And it does the layout on the die on the different logical units to be able to execute at very high efficiency. There's a full array of general instructions with specific machine learning instructions for tensor operations, for control processing, and the data flow architecture and harvesting sparsity. Now, this is really key. You hear a lot about pruning models in deep learning, and that means being able to get rid of a lot of the zero weights. There's a lot you can do ahead of time too, and while it's running. And that's what the overall software and hardware architecture that Cerebrus is providing does. Next slide was fine, thank you. What I want to say is that these frameworks run in containers that are closely orchestrating the workflow between the host processor, in this case, the Superdome Flex, and the Cerebrus wafer scale engines. And they're what do the data movement, rather than having to host the whole data set in the accelerator RAM like you would do on a GPU with HBM2 memory there. Data is instead streamed from the Superdome Flex to the wafer scale, to the wafer scale engine. And that is why we actually have those 12 very high bandwidth links going in that direction. So going back to the wafer scale engine itself, now this is a high level diagram of the way the memory is really across the whole processor and distributed across the processor. Well, let's us get at the SRAM in only one clock. That's essential. Using small batches of batch size 1 lets the system run at very, very high efficiency. And it lets you scale without doing big batch sizes. So for those that have worked on tuning batch sizes to optimize efficiency on GPUs, this is designed to avoid that. It's designed to make deep learning interactive to maximize programmer productivity. And it's just a new way of thinking about things. Next slide, please. The fabric is what we talked about. In this is a very microscopic view into that die of processors and the fabric connections as these reddish orange lines between them. The advantage of connecting this way is that there's no bottleneck. Everything is very densely connected. There's no synchronization problem. Everything just flows at this 100 petabits per second. And we can train it to small batch sizes. Next slide. I want to say just a few words about the Superdome Flex. So this is probably the world's biggest front end. For those who remember other supercomputers, the front end was this little node used to talk to the really big thing. In this case, our front end is fully a supercomputer in its own right. It is 32 high-end Intel Xeon sockets, 24 terabytes of RAM, about 4.5 terabytes per second of memory bandwidth. It is a monster in itself. And the point is that this is fully provisioned to serve the CS1 units at full speed. Internally, there is a crossbar topology. For those that don't know, this is what's called a NUMA or non-uniform memory access shared memory server. It means that every core, every processor can get at all 24 terabytes of RAM in the full system. And that's essential to be able to scale this training up. It means that as a user, you don't have to break up the training set across many different nodes and distribute that and then worry about how do you get those off to the deep learning engine, the whole model can just reside on the Superdome Flex and be farmed off to the Cerebrus at full speed. Next slide, please. So this is just more detail on what the Superdome Flex is. It's really enabling ease of use, high performance, and internally, it also has a lot of internal NVMe SSDs, about 205 terabytes. These we see as caching local data sets for the Neocortex at the beginning. And then later, interfacing this through the HPE Data Management Framework, or DMF, to be able to transparently cache data that comes from Bridges 2 to Neocortex, and to be able to serve many projects at once, many users, and really to enable throughput across the open science community. Next slide, please. The diagram of the system is fairly simple. Bridges 2 is on the bottom. I know you can't see my cursor, but it's a big system. It's over 70,000 cores, over 5 petaflops, a lot of disk, 192 Volta 32 gigabyte GPUs for those who want those for other deep learning training and for other purposes. Then that connects at 1.6 terabits per second to the Superdome Flex. Over that link, data is cached to the Superdome Flex for doing training iterations. That then goes through a 100 gig switch to the to the Cerebrus CS1s. And as we've said, each one of these is independently, up until Neocortex, the greatest training system in the world. Now we have 2 of them, and we'd really like to explore training across them as well. Next slide, please. Paula, would you like to resume here?
Either way, so as Nick mentioned, thank you, Nick. As Nick mentioned, one of the great things about this new system is that it's available to be used through the frameworks that some of the frameworks that are the most popular ones, that is TensorFlow 2 and PyTorch. So we will be expecting that to be supported from day one. The transition from, or the code changes that need to be done in order to exploit and optimize your application for this, for the CS1 will be minimal. And for that, we will be offering comprehensive support. Now, there is also the option to create your own kernels and applications by coding on a low-level programmable C++ interface that is called Layer. So what we see here is it's going to be extremely useful from day one. Now, the element that we have here with the CS1 is that there is a Cerebrus graph compiler, and this is how the application is executed, or what happens before it is executed. You define your model and your training using popular frameworks. There is a matching to a kernel graph that are optimized and know exactly how to place the application on the node, on the chip, well, on the wafer, in such a way that is exploits sparsity and exploits the correct execution of the model. With that, we will be concluding the system architecture part of the talk. And I'm gonna go and then talk about the early user program, which is the way in which we expect those of you who have an application that would benefit from Neocortex to join us. We did have a poll a moment ago that asked explicitly that how many of you have an application that you consider would benefit from Neocortex. I saw a great portion of you answer yes to that question, and we will be more than happy to hear more about your what you're working on and how can we work together. So the goal of the early user program is to achieve scientific progress. We would like to enable that for you. Certainly the early user program is going to work under the same terms and conditions of the whole system, which is you can get access to the system at no charge at all. For the early user program, we will be having a user guide, frontline support and advanced support from day 0. So there will be support from train PSC user support uh, experts, and also certainly from Cerebras and HP. Now, we are expecting the early user program to take place in the fall. So we are targeting, and as we know, there are many moving pieces with the current environment in which we are living, but our target, if everything goes well, is October. We will be releasing more instructions on how to apply to this program through our webpage. So between the next week and the next one, we should be announcing the specific mechanism or process to join us. And then just so we, you know what are the expectations. Our goal is to enable your applications, and in the process, we will ask in return that you provide some feedback. It can be in the form of surveys or just close communication with our experts. Now, once again, the goal here is to produce scientific progress, enable that for you and for the project. Now, I would like to make it a little bit more explicit what kind of applications or some examples of some of the applications that we would like to include in the early user program. If you're working on annotation-based encoder only or decoder only models such as BERT or GPT-2 or GPT-3, please contact us. LSTM models, LSTM-based recurrent neural networks, and also graph convolution neural networks that are keep well in style for graph level predictions. Those are also ideal candidates for our system. So absolutely, if you answer yes to the question, if you have an application that will benefit from Neocortex, please follow our webpage and let us know, or get in contact. You can also just send an email at this time and we'll follow up with you. Now, just so we are all clear, this is our target timeline. This project started in June 1st, so it's very recent. Since then, we have been doing preparatory activities, including system and user environment definition of that, documentation, working on documentation and dissemination, inviting researchers for early user programs. So there are some of you who have been directly contacted because we are aware of applications that you're doing that would benefit from this. But for those of you that are now listening or hearing about this model and want to join us again, please reach out. Now on July 20, we are expecting to accept the applications for early user program. So this more broad invitation to participate. Then late summer 2020 is when we expect to have delivery, installation, and initial testing. And then in the fall is when we expect to advance our early user program and hopefully conclude the acceptance or the official acceptance testing. We are close to the conclusion of the content of this webinar. We will be having additional webinars. In particular, we have one, we're planning one for late August, where we will be diving deeper into the CS1 and how it benefits a specific type of networks or deep learning networks. We will have a PERT 20 plenary on July 29. Please join us to learn more about not only Neocortex, but the other new NSF-funded systems. And once again, we will be releasing more information on the early user program, and that will be officially released on our Neocortex website. The website is definitely the official way to get more updates on our system. And any additional questions, inputs, or requests, do not hesitate to contact us at neocortex@psc.edu. Now I see there is a typo there, so I'll fix that. And when we share the slides, they all will be there. Now, as a summary, we are very excited to deliver this new advanced computing system that is capturing incredible AI hardware technology that once again is bound to transform or promises to transform the AI-enabled research landscape. It's going to be available late this year at no cost for those doing open science. It incorporates 2 Cerebras CS1 systems, very high, or extremely revolutionizing, groundbreaking hardware technology, and then 1 HP Super Flex with 24 terabytes of RAM. And I want to highlight here also that one of our main goals here in this project is to engage a strong community around the new technology. So you will be hearing more from us, and we will be focusing strongly on outreach, training, and user support. Now, I would like to conclude with repeating again that if you have an application and you're interested in participating in this project, please follow the project website or just send us an email right now saying that you are interested and we will follow up. I would like to conclude with extending our gratitude to all those contributing to this project. So NSF, we appreciate the vote of trust to explore these great promising technologies, our partners, Cerebras and Hewlett Packard Enterprise, and then absolutely our team at PSC who are making this project possible. Thank you, and with that, I would like to open the Q&A section of the webinar.
Okay, so Paula, thank you. This is Nick again. We've been monitoring the questions in real time. Some I know have been answered in chat, and I would like to read from a few of them in the remaining 12 minutes and get them answered. Those we don't have time to answer in this session, we will follow up. We'll be posting the answers on the Neocortex website. So if you don't hear yours addressed, we haven't ignored you. Please just check back. We'll be sure to send that link as well. So the first, I've tried to group these as well as we can. So first of all, the first question, I'm sure it had many upvotes on Slido. How much, and this is for Paula, how much does it cost to access Neocortex, and is there help for people who are getting started?
Sure, absolutely. Well, as it has been mentioned during the webinar, access to Neocortex is at absolutely no cost for those whose work can be classified as open science. For those interested that don't fit that specific class, we would need you to send an email to our address, and then we will explore, or we will get back to you with more information on venues through which we could possibly enable access to Neocortex. Now, for those that participate in our early user program, there will be plenty of support, and we are very interested in making sure your application properly runs in Neocortex and runs efficiently. So we will be working closely with experts here at PSC and also Cerebras, and eventually a larger support team of experts.
Okay, thank you. Now, I know you spoke to that to some extent in the presentation, but there's a question that also was upvoted. What are the characteristics of deep learning tasks that should be run on Neocortex rather than on Bridges or Bridges 2?
So in general terms, it would be those deep learning applications that are currently hitting limits. So if there is research that you want to advance and you are needing to kind of bound within what you can do with what we currently offer on Bridges, which includes the DGX2 and also all the other nodes and Volta GPUs that we offer within Bridges, what we refer to as Bridges AI. If there's research that you're currently are bounding to what fits there and you would like to explore additional spaces in the hyperparameter or additional areas in the hyperparameter space, or you want to explore larger models or more complex models or more possibly dynamic models, that's definitely an indication that you should be considering Neocortex or preparing to exploit Neocortex. Additionally, if you have, on top of that, if you have networks that are particularly sparse or that fit the description that we have given in terms of being like encoder or autoencoder only type of networks like BERT and GPT 2 or 3, those are candidates definitely for this system.
Okay, great. And I'd just say if you have things that you would like to run, let us know, and we'll let you know where the roadmaps are and where they can fit.
Absolutely. And I would like to say that in general, if you have questions, like you're not completely sure, then we can also just follow up and explore your specific application, and to start with, help you answer whether or not it's a good candidate for Neocortex.
Yes, so thank you. So there were 4 questions that all have similar feel, and I've grouped them, and I'm going to summarize them. There are 4 questions, and I'll volunteer to take these just to break it up. And they have to do with, can you run hybrid HPC and AI applications using Neocortex? And can you run things other than deep learning on Neocortex? So I'll try to answer those at once. So certainly one of the things we've always been advocating at PSC is heterogeneous architectures to be able to run these converged HPC and AI workloads. So with Bridges 2 and Neocortex, absolutely. You can do the hybrid HPC and AI applications, for example, running CFD on Bridges, and then using Neocortex for doing high performance training to develop surrogate models and so forth. Now, I know that there is some work being done to also be able to do HPC type things on the Cerebrus CS1. Initially, Neocortex is targeting AI, but we'll also be interested to hear in what other things people might want to do and see if there might be a fit. So I hope that helps. Feel free to follow up with us and would be happy to get into more details. So I now have a couple questions I've grouped that I'd like to pose to Sergio, who is our co-PI and Associate Director for User Support. Sergio, there are questions about if the system will be available to the general research community, how to get access. And into this, I will also group questions about deeper training and documentation, such as we'll do through our next training sessions.
Okay, thanks, Nick. Thanks everyone for attending and asking these fabulous questions. The answer to availability, the system will be available, as Paula said. There will be an early user program, and then there will be allocations via the Exceed application process. Regarding the ability to build custom applications, I think, as Paula said, there is an initial set of APIs, basically, and interfaces that will be available from day one. At some point, we do plan to make a software development kit available. As was said before, I think the key really is to understand, for you to contact us and tell us what you want to do, and we will, work with you to, help you do what you want to do as soon as possible. Enlisting our, partners at Cerebrus, so we have, as was said, we have the ability to maybe get into, accelerate some processes with the vendor. Because this is actually a close partnership between PSC, HPE, and Cerebrus. So just let us know what you want to do, and we'll make it happen. In terms of the early user program, as Paula said, the process will be announced soon. In terms of what we will want people to tell us is basically, what progress would they like to achieve specifically during the 30 days of the early user program, which will be part of the acceptance testing. Just, what prerequisites they need, such as data. Again, what do you want to do? So we'll set up a process to ask you these questions and then to stage in projects according to that.
Okay, thank you, Sergio. We also had some very good technical questions. And for these, I would actually like to defer to our colleague at Cerebras, Natalia Vasileva. And there are two questions, Natalia, I'd like to send your way. One is someone who points out that a lot of graph analytic applications can involve very large data sets. And how does the Cerebras CS1 and Neocortex handle that? The second is actually several questions where people are asking about how is performance looking compared to other systems and in general. Of course, we recognize that the system is young and growing, but what can you say?
Thank you, Nick, and hello, everybody. So first on graph algorithms. Yes, you're right that there are multiple algorithms on graph which require the whole graph being kept in memory. But we believe that Neocortex is also uniquely positioned to run on to try some new algorithms with that, because you will have vast memory capacity on super-complex system. So it will be possible to keep the whole graph. We have 24 terabytes of memory in memory of that system, and maybe run some traditional algorithms on that. And then maybe sample some subgraphs for as training samples if you would like to run something like convolutional neural networks on CS1. And for graph convolutional neural networks, CS1 is a really good fit, because for most of those operations, or there are a significant subset of operations which happens on adjacency matrices, which are typically sparse for those graphs. So we see some interesting results when we run, as of today, we run graph level prediction tasks on CS1 system when graphs are not as big, but they have very large number of graphs. So an example of application will be something like drug discovery, when every graph represents a compound and you need to predict some properties of that. So for these smaller graphs and graph level prediction tasks, we run them today on the system and see some interesting results, because again, our advantage of dealing with sparse linear algebra operations. And we have some ideas how we can tackle other kind of node level tasks on very large graphs, but it will be very interesting to collaborate on those and to see what can be done on a Neocortex system as opposed to just CS1. And the second question was regarding the performance. So we see orders of magnitude speed up on different workloads which we run today on CS1. So typically we work with so far we've been working with several customers. Probably the one which we talk publicly about is Argonne National Lab. So their researchers use the system actively today. So we also deployed recently a system into Livermore National Lab, and we have a few commercial customers. I can't talk about their applications or names of those customers due to confidentiality. They don't use typically stock networks, and we are mostly focused on supporting them in their applications. So they typically use the same type of layers. So we run attention-based networks, we run different fully connected neural networks, so 1D convolutional neural networks and many others, but they are not the models which have names from papers. And on those models, we see orders of magnitude speed up compared to existing setup with the either single V100. Many of them run distributed, but small scale distributed setups like within a single system.
Natalia,
answers. Yeah.
Yeah, thank you. I don't mean to cut off the questions. There are many, many more good questions that we will answer on the Neocortex website. But we are at the top of the hour, so we'd like to respect everybody's time and thank you for attending. Paula, do you have any closing remarks?
Well, thank you all for attending the webinar. Thank you, Nick, Sergio, Natalia, and all those that are making Neocortex possible. We will make sure to follow up with all questions and also publish on our project website the results of the polls. I think it's interesting for everybody to see where this audience stands regarding some of these questions. So thank you all, and we look forward to working with those of you who would benefit from this great system.
Okay, thank you, everybody.
Thank you. Bye-bye.
Thank you. Bye-bye. Have a great afternoon.